Hi students, so 5.7 rational functions, and really this is the first half of a 2-point job because today we're going to focus on rational functions and partial fractions, how to manipulate the form of these algebraic fractions so they are easily integrable, anti-differentiable, and then tomorrow we're actually going to focus on that process. So to begin with, what I'd like you to do is just take this one on the board right now and see if you can find A and B. So you'll have done this before. What is A and what is B in order to equate both sides here. Have a go, then when you're finished, unpause the video and we'll carry on. Alright, so that process that you just practiced is part of what we call taking rational functions and representing them as partial fractions. The purpose of doing that in this case is that the output of that process, those two fractions in that question, that the ones involving the A and the B, they're things that we know how to integrate, whereas the original function we don't. It's too hard. So what we're going to practice is going through the process of taking different rational functions, representing them as partial fractions, and then if we do that, we can then integrate them tomorrow. So first up, what is a rational function? Well, it's a rational function that has a polynomial on the numerator and a polynomial on the denominator. So there could be all sorts of different examples, but 3 over x squared is an example, or 3x to the power 4 plus 7x over 4x cubed plus 2. Those are both both rational functions because the numerators and the denominators are both polynomials. So, a couple of other bits of notation. If the degree of the numerator is less than the degree of h of x, then we call f of x a proper fraction. So the degree, that's the power, on the numerator is less than the power or the degree of the denominator. So of these two that I wrote here, this one is proper because the degree of the numerator is 0 because it's x to the power of 0, whereas the degree of the denominator is 2. And this second example here, well, this is improper, and that's improper because the degree of the numerator is 4, but the degree of the denominator is 3. And the key thing to note here is that it's also improper if the degrees are equal. So it's greater than or equal, then we have an improper fraction. Okay. And what are we trying to do here? Well, we're trying to write rational functions that we see that are a little bit complicated in terms of simpler fractions, because if I can write it as something in this form, I know how to integrate that. In fact, if my fraction is k over ax plus b, linear denominator, well then straight away I know it's going to be k over a log e of mod ax plus b plus c. Hopefully that's familiar to you, and you could have worked that out for yourself even if it took a little bit longer. So there are 3 forms that we're going to look at today. We're going to look at distinct linear factors, and what we're talking about here is the denominator, so 2 different linear factors on the denominator. We're going to talk about repeated linear factors, so that's this bit, the fact that I've got x plus 5 all squared, that's the repeated linear factor. And then we're going to look at an irreducible quadratic factor. And irreducible here means no real roots, or in formal language, or cannot be factorized over r, the real numbers. In other words, we've got a quadratic factor that we can't split into linear factors. because it's got complex roots. So first case is going to be almost straightforward. In the second case, we'll come on to it, but where we've got a repeated linear factor, you start with your a and your b as you normally would with the two factors, but then you're also going to need a third fraction c, which is over the repeated linear factor. So in this case, x plus 5 squared. And we'll see when we do an example exactly why that's true. If we have an irreducible quadratic factor, so the x squared plus 5 here, we need to fix that with another constant, but what we do here is we end up with bx plus c on the numerator. So these are our three forms, really. We need to memorize these, and then depending on what the denominator of the question is like, we know exactly which form we need to take. And I guess just in this next box here, we can generalize this process, because actually if I have a repeated linear factor where it's not squared but it's cubed, or it's to the power 4 or it's to the power 5, then we just need a fraction to go with each of the powers. So if I were to generalize this, you would have, like, if it's to the power n, a over x minus a, and then you'd have a b over x minus a squared, and then you'd have a c over x minus a cubed, and then you just keep going until, you know, you get to n, x minus a to the power n. And you might see a question where actually there's a cubic repeated factor. That is possible, and in which case you'd split it into these three terms. What we're going to look at when we answer the questions is two simple methods for doing this. Substitution and equating coefficients. And what I'd say to you is we're going to look at both, because sometimes one is much easier than the other, and in fact for some questions you might want to just use a combination of both to answer them as quickly as possible. So here's the question from the beginning, the first slide, and I'm going to just do it straight away. So the way I'm going to lay this out is I'm going to say I know, using, you know, this form, that I can write this as a over x minus 1 plus b over x plus 3. And then what I'm going to do is I'm going to imagine converting this right hand side into one fraction. And if I do that, I'm going to have to multiply the left hand fraction by x plus 3, because then the denominator is going to be x minus 1 times x plus 3. And then I'm going to multiply the second fraction by x minus 1. So overall, that's going to give me a times x plus 3 plus b times x minus 1. And that's all going to be over the same denominator, which is this. But for my purposes, I don't need to worry about the denominator there, because I know they're the same. That's the point. So just looking at the numerators, what I would know is that 3x plus 5 is a times x plus 3 plus b times x minus 1. And in order for this to work, that has to be true. So this first step is the same for both of my methods, but the first one I'm going to look at now is substitution. And what we do here is we use the roots to help us eliminate one of the variables and solve for the other one. So the first thing I'm going to substitute in is x equals 1, because if I do that, I've chosen x equals 1, on the right hand side here this term disappears because the bracket becomes 0. So I substitute in x equals 1, left hand side 3 times 1 plus 5 is 8, equals a times 1 plus 3, which is 4a, so a is 2. And we've straight away found one of the roots. The second value I'm going to substitute in is minus 3, because then the a disappears. Minus 3 times 3 is minus 9, plus 5 is minus 4, and then that equals minus 4b, so b equals 1, which means, to finish off my method, f of x equals 2 over x minus 1, because a is 2, plus 1 over x plus 3, because b is 1. And then if I were to ask to integrate this, I can do so, because I know the integrals of those two terms. Just really quickly, Here's the equating coefficients way of doing the same question. So equating coefficients. Starts off the same way, but then what we do is I'm going to look at the x coefficient. So the coefficient of x on both sides. I've got 3, and then on the right hand side I've got a plus b. Then I'm going to look at the k coefficient, the constant. The left hand side I've got 5, and on the right hand side, well, I've got 3a, to expand this bracket, and minus b. And then what this method involves is us solving these as simultaneous equations. If I add both of them, I'm going to get 8 equals 4a. So that tells me that a is 2. And then I substitute into the first one, sub into 1. A is 2. 3 equals 2 plus b. So b equals 1. And that's an alternative way to do it. And you might say, oh, well, the substitution is much easier in this case, and I agree, but in some cases, actually, a combination of both is the best. So what we're going to do now is there's 2 on the back, and you won't be surprised to hear that they follow those 2 forms. So we've got a repeated linear factor, and we've got a irreducible quadratic factor. And what I'd like you to do now is to try both of those, and then I'll show you my solutions. So pause the video and have a go. Assuming you paused the vid, you've had your own go, here are my solutions, and I've done them both ways. So the form for a repeated linear factor is that we need the x minus 1, sure, but we also need the x minus 1 squared. Then when I imagine writing the right-hand side as a single fraction and making the denominator x minus 1 squared times x plus 1, the numerator of that equation is going to be 2x plus 10 on the left, is a times x minus 1 squared, plus b times x minus 1 x plus 1, plus c times x plus 1. We've got those 3 terms. And then depending on which method you used, either using substitution, I'm going to sub x equals 1 and x equals minus 1 to give me c and a. And then for the third value, this is a little trick. Probably the easiest thing to do is just sub x equals 0. You can always do that, and that's going to give you a really quick equation involving a, b, and c. And then you can substitute in your values of a and c, and it gives you b. So overall, putting those in, a equals 2, b equals minus 2, c equals 6. Here we go. For equating coefficients, your 3 coefficients that you're going to look at are the x squared coefficient, the x coefficient, and then the constant coefficient. That gives us 3 simultaneous equations, but luckily they're quite easy to solve. And then once you've got the first value, you can just substitute that into the other equations to get the other ones. For the irreducible quadratic, here we only have 2 terms, but we have a bx plus c on the numerator of the quadratic. And when I do that thing where I compare the numerators on both sides, I would get x squared plus 6x plus 5 is a times this numerator plus bx plus c times this numerator. And here we see the reason why we need this bx plus c, because what we need is a quadratic term from here to balance the one from a and allow us to get the x squared coefficient to be what we need. So when I've substituted in here, I've substituted in x equals 2, because that will allow me to find a, because the second term disappears. But then from that point, I just need some simple values, and I'm going to choose 0 and 1. If I substitute in 0, I get a quick equation in terms of a and c, and I can find c. And if I substitute in x equals 1, well then I'm going to get an equation in terms of a, b, and c, but I substitute for a and c, and it tells me that b is minus 2. So overall, I get f of x is 3 over x minus 2, take away 2x plus 1 over x squared plus x minus 1. And you can see here I made a bit of a hash of it the first time, but it's always worth you just checking, just like once you get your answers, just mentally checking that you're going to get the right coefficients on the left so that you don't make a silly mistake. Equating coefficients is not a bad one here, because obviously you can see substitution starts to get a bit more complicated. Your equations come out, you get this nice thing where the first equation just involves a and b, and the third one just involves a and c, and so you can substitute those in. You get a couple of fractions, but it's not too bad, and quite quickly you get a equals 3, and then from that b and c just fall out. So yeah, look, either method good, and the important thing is we end up with things that we can integrate. So then the very last thing for today, when we encounter an improper fraction, it won't go straight into partial fractions. What you first need to do is kind of, just like you would if you had an improper numeric fraction, just like if you had 17 over 3, you would write that as a whole number and then a fraction. We need to do exactly the same thing, but to do it for our algebraic fractions. So if I'm looking at this, which is definitely improper, because the degree of the numerator, the 5, is bigger than the degree of the denominator 2, so it's improper, I need to do this division. And the best way to do it is, because you're going to get a remainder, it's not going to go exactly, is to do it in terms of long division. Obviously in some cases you might find a slightly easier way to do it, but in this case I'm going to fall back on long division, and what I'm going to do is I'm going to divide x5 plus 2 divided by x squared minus 1. I think, okay, well, how many times does the leading term go into the leading term? And it's x cubed times. So x cubed times x squared is x to the power 5. So then I'm going to have to imagine, okay, I multiply the whole thing by x cubed. That's going to give me x to the power 5 minus x cubed. And then I'm going to take that away from what I had here. And if I take that away, I've got a minus of a minus, sorry, negative of a negative. So that's going to give me x cubed. And then I've got the plus 2. So now I'm looking, okay, well, how many times does the x squared minus 1 go into the x cubed plus 2? And looking at the leading terms, always the leading terms, x squared times x is x cubed. So I've got to put a plus x on here. Then we multiply the whole thing by x and see what we're left with. It's x squared minus x. We subtract, x cubed minus x, and we subtract that, the x cubes cancel, and we end up with positive x, minus minus, positive plus 2. And here, because the order has gone below the x squared, there's nothing I can do. So what that means is that x to the power 5 plus 2 divided by x squared minus 1 is x cubed plus x, with a remainder of x plus 2. So in terms of the original question, I split this into kind of my whole number part and then my fraction. So the whole number part is the x cubed plus x. And then I also have my fraction part, which is the x plus 2 over x squared minus 1. And then what I'm going to do is I'm going to do the partial fractions with this. So partial fractions with this part of it. Quick way to do it. So x squared minus 1 is x minus 1 times x plus 1. So what I know here is x plus 2 over x squared minus 1. That's going to be a over x minus 1, a over x plus 1, plus b over x minus 1. And then looking at the numerator of the combined fraction, x plus 2 is going to be a times x minus 1 plus b times x plus 1. And then substitution, if x equals 1, then I'm going to get 3 equals 2b. So b equals 3 over 2. And if x is minus 1, left-hand side is going to give me 1, and that's going to be minus 2a. So a must be minus a half. And then I substitute those back in. So what that tells me is our original function f of x. We've got this whole number part, x cubed plus x. And then we've got our fractional part, which is going to be b is 3 over 2. So 3 over 2 times x minus 1. Minus a half, 1 over 2 times x plus 1. And this, again, is something that we can integrate because we can split it into 4 separate terms and we can integrate all of those. So hope that that process is simple enough for you. The little tip at the bottom is that actually your CAS calculator for the big exams can just do this for you. And so if you end up with a question like this one that we've just looked at, well, you use interactive transformation expand and choose partial fractions, and then happy days, here we go, it does this whole process for you. So we need to be comfortable with both, as with all of this stuff, but that will save you some time in the longer exam. Right. As normal, have a go at the questions, and then in the next lesson we'll look at actually doing the integration with some of these. Good luck.